All right, yes, so I hadn't realized I'm launching off week 2. I hope your excursion was fun and without mishaps yesterday. Okay. All right, so yes, I was asked to talk about secure compilation. While preparing for these lectures, I have realized that there's no way I can talk about secure compilation without talking about correct compilation, which I think will serve you guys better. So I'm basically going to sort of start off by motivating what secure compilation is all about, but these lectures are going to sort of transition between, showing you proof techniques for proving compiler correctness, and then trying to show you what kinds of techniques we need in order to prove that a compiler is also secure. And then my plan is today, to sort of motivate. Then I will take a particular compiler pass, a small one, something I can fit in a lecture. We'll cover closure conversion, and really walk you guys through the details of how one takes a small translation and prove it correct, and then how start to think about what it means for a translation like that to be secure. And then I'm hoping, depending on how things go, that I will be able to, in my last lecture on Wednesday, be able to just sort of step back and give you guys an overview of what the state of the art is in both compiler correctness right now, compiler verification, as well as, survey a bit of what's happening in secure compilation, just so you have pointers for somewhere to go afterwards, right, for more reading. Okay, so that's my plan. All right, so anytime I'm not loud enough, please just say so, all right? Sometimes I might forget. Okay, so secure compilation. So what is it about? In a nutshell, this is about building compilers that ensure that any security properties that you had available in your source language, in your source programs, are preserved after compilation in your target programs. Okay? So that's the basic motivation. And now, what I want to do is kind of go through a few examples and talk about why this is normally just not the case. Okay, so let's start with just a snippet of, and these are really minimal examples cut down to fit and, so you can kind of easily understand them. But here's some Java source code. All right, so Java is a language in which we have private fields, right? So right there, I have an account class, and in that, I have a private field, which is the balance in the account. And I've sort of constructed this example so that there's only one method. It's deposit. All right, so you can call deposit and deposit an amount which gets added to the balance. Great. Now, just let's imagine translating this code down to some other language. And I won't go all the way down, to anything too low level, but imagine that we translated it down to C code. Okay? So it might look something like this. We might want to compile it down so that in our C code we represent an object of that class with a struct. And so we have this struct type account T, which has a balance and it has a deposit function and so on. All right, and basically deposit calls this function deposit f over here, which does exactly what we expect the method at the top to do. Okay, so can anyone tell me why this compilation might not be secure? Yes? The balance is not private, right? There was this concept called private. It was part of the Java, it's an abstraction, right? In the Java source language. It ensures that any clients of this class will not be able to go in and just directly read the balance. That's what it means to be private. Right? But when we compiled it down to C, C doesn't have a notion of private variables or secure variables that cannot be read by a client. And so we've compiled it down to the struct, and now it's simply an integer. And what can happen? Well, some C code, suppose that, in Java you can call that account, once you have an object of an account, that gets compiled down to an object, essentially, a structure account T of type account T. And then if C code has a pointer to that, you can just do some pointer arithmetic and go in and read that field, right? It's really simple. So it's not private anymore. Okay. So secure compilation is about how do we mitigate things like this, right? How do we ensure that any kinds of guarantees, information hiding, etc., that you have available to you in the source language is preserved after compilation? And here it clearly is not. Okay, so let's go on. I should have done this animation before. But what's important here is the fact that even as I described to you what the problem is, I had to say that suppose you took a pointer to a count t and gave it to some other bit of C code. I'm imagining that other bit of C code as your attacker, the context that you link with, some other code, all right? And throughout these lectures, I'm going to focus on secure compilation where any behavior that my attacker can do is modeled through writing some target level code that interacts with the compiled code. Okay? This doesn't capture certain things, like it doesn't capture attackers that might use side channel attacks. Okay? I'll come back to that in my final lecture and briefly talk about it, but most of these lectures are going to be about, I have some component, it's not a whole program, I've compiled it down to the target, and now it has to link with some target level code that is essentially my attacker, and is able to do things that no source level attacker, if you will, or source level client would have been able to do. Okay? All right. So, this kind of problem arises because we have this gap between source and target abstractions, and basically we need, if we're going to ensure secure compilation in this scenario, we need some sort of a mechanism to hide this balance once we've compiled it to the target, right? How might we do that? And sort of what I want to focus on is how do we preserve such security properties? How do we ensure security in this scenario? Do we augment the type system of the target language so that it understands what private is? But then we might have to do this for every single feature in our source language, right? And so think about how we write compilers these days. We normally like to have common compiler backends, right? You have many different languages that you compile to LLVM. Well, LLVM better be able to understand all of them if we want secure compilation for many different languages to the same target, right? So there's that. So how can we express source properties in the target? I'm going to talk about this as I go on. Okay, so let me just give you a few more examples before I dig into technical things. So what I want to do is just go through a bunch more examples where source level abstractions aren't preserved when we compile to the target and the target is able to launch attacks. And what I want to do in this next set of examples is point number 2. I want to start seeing how this notion of security that we are relying on in each example in the source is actually an equivalence property. That's how we would express it. Okay? All right. So here's an example of confidentiality. All right? This is kind of what I had in the last slide. I have a private secret. It's an integer. And then set secret sets that secret to 1. But notice that it is setting a private field to 1. Right? So no client should be able to know that that private field is now 1. Right? Okay, so this is very much like the example that I kind of started out with. A private field is, presumably you can think of it as being compiled to some low-level target, and I want to make sure that it remains hidden. But what I want to focus on is how do we express confidentiality? My slide says I expect confidentiality. The secret should remain hidden from clients. You should not be able to tell once set secret returns, the secret is now 1. Andrew Myers has been here, so how do we express confidentiality properties? Non-interference, exactly. And what does non-interference say? It says that, suppose you have a program, if it has some secrets, then if you change, or let's say high security data, if you change the contents of those high security variables, you should not be able to tell the difference, right? So just for now, I'm going to say that intuitively, this code, if confidentiality holds in the source language, then this code should be equivalent to this code here, all right? Where my secret is some other value, it's a 0, all right? If these two are equivalent, then yes, indeed, just for this particular example, and in general, we would express it with non-interference, but here, just for this little example, confidentiality holds if these two pieces of code are equivalent, all right? So this is, I'm trying to give you a sense of, properties where what confidentiality even is captured through a notion of equivalence in the source language, okay? All right. So if I want to preserve this confidentiality, that means that these two pieces of code after compilation better still be equivalent when linked against any target level attacker. Okay? Now, of course, target level attackers will have more power. For instance, they won't understand private, as the example that I discussed before already. I already talked about it. So in a sense, if we want to preserve confidentiality, we have to preserve equivalence, this particular equivalence, or non-interference in general. All right, let's talk about integrity, which is sort of the dual of confidentiality. So here I have a proxy method which takes a callback. Okay? The point here is it takes a callback, some function, some code from the attacker. Imagine that the attacker is going to write that code. All right, so then proxy sets secret to 0 and then calls that other function. All right, so now intuitively, we're in the source language, right? Intuitively, the way this code is written, you can tell that there's no way that callback would have access to secret, right? I mean, someone wrote it and passed it to me before I ever even declared that there was a secret variable equal to 0. That's why they should not have access to it, right? Okay, and then after I call the callback, I return 0. All right, so this idea that this other code, the callback code, does not have access to my secret variable, right? I'm sort of relying on that for integrity in a way in this language, right? I'm relying on it and sort of assuming that even though after I declare secret, I call callback, there's no way callback is going to go and mess with the data that's sitting in that variable. It just can't. It doesn't have access in the source. So if we want to express this again as an equivalence property, it should be equivalent to this other code, right? What is this other code doing? Well, after callback, I am checking if secret is 0. Okay? And then if secret is 0, I'm returning 0. Otherwise, I'm returning 1. What is it? So what I'm saying is that if integrity holds, these two pieces of code must be equal. Must. No matter what callback you pass me. No matter what attacker code you pass me, right? Okay, and you can tell, right? It will be because if callback does not have access to secret, then secret will always be 0 and we will always return 0. That is just the path that we will take through the code. So these two pieces of code should be equivalent. All right, so in order to preserve integrity, we need to preserve things like this. Of course, once you compile that original code down to the target language, what can happen? Yes?
The variable secret could be on the stack.
Exactly.
So find it.
Precisely. So the variable secret is simply on the stack. When we compile from a high-level language where there is no stack into a low-level language where these things are sort of manifest, then the code can just sort of reach down the stack and go and edit, store a different value right there where secret is supposed to be. Right? Okay. All right. So if we want integrity to be preserved, we want this equivalence to be preserved. Next example. So this is a little bit funny. In high-level languages, we normally have this assumption of unbounded memory. Especially garbage-collected languages, we don't worry about it. We don't think about it. Okay. So what this code is doing is, and the point here is that, of course, when we compile, we don't have unbounded memory. Memory is finite. So this is a little bit, idealized, but just imagine that you have this function kernel that, again, takes a callback, and there's some number n, which the attacker is passing me again. So I'm giving the attacker maximal power to maybe do something with this. So what I'm doing is I'm allocating n new objects, all right, using up a certain amount of memory. And then I'm calling the callback function. Now, just hypothetically, if in the target language you run out of memory after allocating n objects, then if that callback code allocates another object or another few objects, then you will never get to that security relevant code at the bottom. Right? The program will crash before that. Will run out of memory before that. Whereas in the source language, I expect this to always succeed. I will always be able to run that security relevant code that's at the bottom before I return. Right? So how should we capture this as an equivalence? Well, essentially, that code should be equivalent to this code where I don't allocate anything at all. Right? So in this case, if we want to make sure that our security relevant code is in fact executed, these two pieces of code better be equivalent. They usually are. We fully expect them to be in the source language, given the abstract, the mental model we use for the source language, but they're not after we compile. Or they could not be. Okay. Another one that we don't even think about is memory allocation order. So here we're allocating two different objects, right? One being assigned to X, the other to Y, and then we're returning X. The order in which we allocate them should not matter. Y is not even visible or accessible from any client. Okay, but if you compile this code down to a target language, an attacker could guess in a low-level language what the allocation scheme is. They could use that to sort of fiddle around, do some address arithmetic and go and mess with the object Y. And you can think of this as partial code, like maybe this Y is sort of local to me and I want to store it in a private field or somehow I want to keep it secure. But after compilation, the target might be able to mess with it. Okay, so here, thinking of this as an equivalence, really, it ought to be the case that I'm allocating two objects. Who cares if I call one X and the other one Y, right? X is being allocated first and Y is being allocated second, and these two pieces of code, whether I return X or return Y, they should always behave equivalently in any context, right? For my assumption about memory allocation not mattering to be correct. Okay? All right. So this exercise that I'm doing with each attack saying how could we attack it, but then also saying how do I express this property that I have in my head as an equivalence? We don't normally think of these properties that we have in our head as an equivalence. It's only when we go to prove formal meta theory about languages and so on that we might do proofs like non-interference and so on, right? But this is just to motivate that this is going on all of the time, in a sense, because programmers rely on this in their source languages. Okay, and there are other examples as well. So here I have a class pair which has private fields first and second, and then there's a get first method. And at the bottom there's a class secret which has a secret. If we compile this down to a language like, to assembly, let's say, or to C, we could take that secret, an object of class secret, and simply pass it to the get first method. And what will we get out? The secret value, right? It's just such a simple thing. What's happening here? Well, in the source language, everything is typed. When we call get first, it takes a this pointer, meaning a pointer to a pair object, right? But in an untyped target language, I can just pass it this other, an object of class secret, right? Because I don't have types in the target language to tell me that this is an operation that should not be possible. Okay? All right. And this kind of a danger is a big thing, right? When we go from nice, high-level typed, strongly typed languages, which give us all sorts of guarantees, whether it's about confidentiality or whatever else, or there's some high-level structure to the code that I'm relying on to make sure that, for instance, callbacks cannot access that secret variable that's on the stack. All of these things that as they get compiled down to the target, if the target is untyped, then you don't have a way of ensuring things that were guaranteed by the type system in the high-level language. And of course, the other thing I put up here is, of course, security type languages. Something like GIF, where you actually have high confidentiality and low confidentiality variables. If you compile to an untyped target, those high and low annotations are gone, right? So an attacker could go in and read a high security variable. And then there are other things as well. This one I was slightly alluding to before. You can do certain things in assembly with the control flow. You can totally mess it up. So in an assembly language, a call and a return are both just jumps. One looks just like the other, right? Okay, in a high-level language, we have this beautiful call and return structure. I call a function, I expect it to come back to me, right? Okay, but once you've compiled down into assembly and everything is just a jump, you could have some assembly code attacker that gets access to a certain pointer and totally, instead of returning, just jumps somewhere else and disrupts the control flow and tries to use that to launch some sort of an attack or to disrupt invariants that you might have needed, that you were enforcing essentially through that call and return structure somehow. And then, if you have something like call CC, first class control, in your target, you can capture the continuation in a target language, and then you can use that to leak data. Okay, so there are all sorts of awful things you can do. Okay, so that's just for examples. And really what I've been trying to get to is, I want to talk about security properties that are expressed as some form of equivalence, and then talk about how to preserve that equivalence. So in this series of lectures, has anyone put contextual equivalence on the board? No? Okay, I had a feeling. All right, so let's talk about contextual equivalence. So given any language, suppose that I want to say that two components, E1 and E2, let's say they have some type tau, are contextually equivalent in that language. All right? What this basically means is I want you to think of the program expression E1 and the program expression E2. You can think of them as components. And what I have in mind is that if I have a whole program, all right, with a single hole in it, right, think this whole thing is a program context. What I have in mind for this general notion of equivalence for my language is that given any program context that I can put E1 into, if I run the program with E1 in that hole, then I get the same observable behavior as if I run the program with E2 in the hole instead. Okay? A classic example of this might be, let's say you want to implement a stack, all right? And you have a stack interface, let's say in Java. And you can write down two different implementations for a stack. One implementation might represent the stack as an array, the silly first one that you do perhaps. And another implementation of the stack might represent the stack as a linked list, right? If you've done your job right, you can look at that code and say, yeah, these two should be equivalent, right? Which means what? Which means that if I tell you that, you can use a stack interface, here's an implementation of the stack interface, and you feel free to use this stack implementation, you should not be able to tell the difference between those two implementations, right? You can't look at what's sitting inside, right? So it's that idea of representation independence is a really powerful concept, and, we sort of think about it in terms of contextual equivalence. Yeah. No, it does not. Excellent question. Yes. So the question was, does this equivalence, contextual equivalence that I'm about to put on the board, also include time complexity? And the answer is no. When we define contextual equivalence, we normally ignore time complexity. And I have another bullet coming up about that. So, okay. So let me first just talk about contextual equivalence. Normally, we set this up so that we say, well, if this is a component, then it might interact with its environment in certain ways. It might have some free variables. So I'm going to put a gamma here. So imagine that E1 is a component that has type tau under environment gamma, and E2 is another such component. Again, it has type tau under gamma. All right? So we say that E1 and E2, which are both well typed in the same environment and have the same types, we say that they are contextually equivalent if for all contexts. So generally, if we ignore types, we simply say for all possible contexts, it should be the case that C with E1 terminates if and only if C with E2 terminates. Okay? In an untyped language, that would be your definition of contextual equivalence, assuming your language is non-terminating. Okay. So in other words, we're just concerned with what we can see, right, through our observations. Okay. In a typed language, we normally don't like to link well-typed code with an we want to make sure that our well-typed context, when linked with our well-typed component, gives us a well-typed whole program, right? We want to make sure that we only run well-typed whole programs. So we need to make sure that this context has a hole of the right type, that it is a hole into which I can stick something of type tau. Okay, so we normally write that as C for all possible contexts of the right shape, of the right type, such that the whole of the context is willing to take terms of type tau that type check under an environment gamma, and gives us back a closed program. We can make this of any type tau prime. Or I could make it int. I could make it a base type of the language. It doesn't matter. Okay, so what does this say? Well, two well-typed components are contextually equivalent in any program context. If given a well-typed context that can accept E1 or E2, they both terminate or they both diverge. Now, at this point you might say, well, why is it enough to just terminate or diverge? What about other observations? What if I'm printing to the screen? What if I'm updating memory and all of that, right? So this general definition, I've shown it to you here, in essence, for a simply typed lambda calculus that's non-terminating. Let's say you have recursion in it. But you can tweak this to languages which have memory and so on. I won't show you the more sophisticated version of contextual equivalence, but it scales rather nicely, right? One other thing to say is that if your language is terminating, then is this the right notion of contextual equivalence? No, right? Because I'm not giving myself any power to tell the difference between two things. So this is a subtle difference. If you are working with a language in which all programs terminate, like the simply typed lambda calculus with no recursive functions, no recursive types, then you need to make sure that you are able to tell the difference between these two programs. And so normally we do that by saying, you could take a base type like bool or int, right? And say, for all possible contexts that give me a whole program that terminates with some ground type, okay? If I stick E1 into the whole, I get the same value. Oops. This evaluates to V if and only if C with E2 evaluates to the same V. Okay? So if you run the program with E1, you get a true, then you get a true with the other component. And similarly for false. Okay? You get the same final base type answer. And this is kind of important to pick a base type here, right? Because if I put a function type here, for instance, then I wouldn't be able to check that V1 and V2 are equivalent. I would sort of be demanding that they're syntactically equal, which is not what I want. Does that make sense? Okay. All right, so that's contextual equivalence. I'm going to be talking primarily about how do we preserve security properties, how do we do secure compilation, such that contextual equivalence of the source is preserved. In other words, if I have two programs, ES1 and ES2, that are contextually equivalent at a source type in a source environment, then after compilation, if I compile these down to ET1 for target and ET2, after compilation, I want it to be the case that they are contextually equivalent. This is source contextual equivalence. This is target contextual equivalence with appropriate translations here. I'll just write it as plus. Okay. What's the difference? Why did I put an S subscript here and a T subscript here? Well, let's go back to our definition. That is a definition that is specific to a language, right? So whatever my language is, if I'm in the source language, if this is source contextual equivalence, then all my terms and my contexts and my types, everything is drawn from the source language. But if I'm talking about target contextual equivalence, then all of a sudden I'm talking about linking with target contexts. And there might be many more ill-behaved target contexts than there are source contexts, right? Or many more target contexts that can do things that is not possible at the source level, right? Okay. And now I just want to say that contextual equivalence, I've written it so generically up on the board, but this will obviously differ depending on what your source language is. If your source language is C, you're getting fewer, in some sense, source level abstractions that guarantee security. If it's something like Galena, right? If you're writing code in Coq, then you have a very strong assumption about what kinds of contexts you are linking with, right? So for two ends of the spectrum. Or if you're in DSLs, you might have a particular structure or termination requirements or whatever else, and so on. So contextual equivalence can be very, very different depending on your language, and therefore you get different guarantees. So now I had a question. Oh, actually, yes. So To me, secure compilation isn't just about preserving contextual equivalence from the source. It's a generic term. You can say a compiler is secure because it preserves some sort of observer-sensitive equivalence, the kind that we use to express non-interference properties in security type languages, right? So in that case, my compiler is secure, not if it preserves contextual equivalence, but perhaps there is some observer, all right, over here, and these components, maybe it's a high security observer. Low, let's make it low. If these two look equivalent to a low security observer, then I somehow want to make sure that that the compiled code looks equivalent to low security observers as well. The problem is, do I have a way of expressing this equivalence between, like when do two things look equivalent to low security observers? If I don't even have a notion of low security observers in my target, then my first task would be to actually try to formalize what the property is, right? Okay, but nonetheless, it's a form of equivalence preservation. And then your question about resource sensitivity, right? Am I taking timing into account? So there you can clearly see I am not taking timing into account, unless I've sort of somehow built an operational model for my language that is counting cost, and cost is an observable. There, cost is not an observable. You can, E1 could be far less efficient than E2, right? And that's often a very important use case for us. You might write some code and later replace it with code that you believe runs faster but is equivalent, produces the same answers, produces the same outputs or observations. So when we talk about resource sensitivity, so we can again generalize this picture so that we are talking about a different form of equivalence that is somehow sensitive to resources. But you would have to formally state how you are counting resources and so on. You need some sort of a cost semantics in order to do that. Okay, I will not be getting into that stuff. All right, so I want to talk briefly about different compilation targets and threat models. So how much you need to protect yourself sort of depends on what you are compiling to. Or how much you need to protect your compiled component depends on what language you are compiling to. All right, so an assumption I'm using here is that whatever context I link with is my attacker, but that context has to abide by the rules of the target language. If the target language is typed, that context probably has to be far more well behaved than if the target language is untyped. Okay? So how much you need to protect yourself sort of depends on what your target language is, what abstractions it already has. Yes?
Just to clarify,
yeah.
All of this is presupposed on the attacker having access to your binaries, correct?
Well, you can say that a compiler is a series of passes, right? I would like to compositionally sort of show that every pass is preserving the security property of interest at the source level. So at the very bottom, yes, binaries or assembly, but really I want you to think more abstractly in terms of every pass needs to be secure, so that we can get all the way down to that assembly or that binary. So we're going to be doing this exercise, at least for these lectures, at a rather high level. So I'll be doing closure conversion, which means that my target is not a binary at all, yet. Yet, being the key thing. And actually, that's a good moment. So you're worrying about security at the binary level. Here's how I often think about it. The kind of secure compilation I'm talking about models attackers as a context, right? How is a compiler set up? Let's say you compile a component. That's the only time when any of what I'm saying is interesting, right? Because it's going to still be linked with something lower level. It's not a whole program yet. If it's a whole program, it's not going to be linked with any attacker. At least that's my mental model for these lectures, all right? So it's not going to be linked with anything else if it's a whole program, and we're all set. We don't need to talk about proving this property. But if you're compiling a component, it gets compiled down to some target. At which point in your compilation pipeline do you link with all the other code? When do you actually have a whole program? That is the level until which you need to prove that security is preserved. After that, you don't need to care. You can just go ahead and prove that your compiler is correct, and that will be enough to ensure a fully verified pipeline. Of course, then you might start to care about side channels, but I'm not going there. Does that make sense? Any follow-ups on that? So secure compilation is critical when compiling components because they still have to be linked with low-level target contexts that can behave in ways that are unexpected at the source level, right? So in some ways, I'm trying to say, hey, my mental model is that I'm going to have my whole program before I get to the binary level, maybe at the LLVM level. right?
But my point was that if the attacker has access to your code, couldn't they just run it through a disassembler and then modify it themselves? You have to rid it of the security problems we work so hard to guarantee?
Yeah, so what exactly? Well, I'm assuming that the attacker is a program, right? Is target code. That's why I keep talking about that context. That is code. The attacker is code. So even if it has access to my binary, it's only interoperating with it. That's what I'm trying to get at. Okay? It's not a person. Okay. Or the person needs to make sure they can write the code that does the attacking. All right, so now, there are different ways of enforcing secure compilation. So one idea would be, why don't we all compile to, let's say, typed assembly languages, where we can use the type system to enforce certain guarantees and make sure that some of the examples that I showed you, right, that we can preserve those security properties if we do a type preserving sort of compilation. Another way of ensuring secure compilation is through every time we compile some code, let's say it has some type, we want to perhaps wrap it with some kind of dynamic checks, so that when a context interacts with my code, it has to go through some sort of a monitor or a wrapper that is always going to check every interaction that the context has with my compiled component. Okay? That, of course, can get expensive. But, of course, static checking has the problem that you have to show that your target context type checks before you link with it. So they both have pros and cons. And one of the things that I want to get to, actually very quickly now, is why proving these kinds of secure compilation results are hard. Right? Ultimately, it comes down to the fact that you are linking with some target context. And you need to show, in order to show that equivalence of ES1 and ES2 implies equivalence of ET1 and ET2, you have to show that given any target context, these two are going to, that context with ET1 is going to behave the same as that context with ET2. Which means that in order to prove that this target context is not doing anything more than what a source context can do, you somehow end up having to back translate the behavior of or the functionality into a source level context in order to prove to someone that yes, my target attackers are being given no more power than my source level ones. Okay? So that part is hard. Imagine back translating assembly into ML, right? Yeah. At least without any constraints. Okay, so to jump ahead, I'm mostly talking about, as I said, contextual equivalence, preserving contextual equivalence. And when it comes to contextual equivalence, we have a term, fully abstract compilation. So we say that a compiler is fully abstract if it is equivalence preserving. In other words, if the blue E1 and E2 at the source level are contextually equivalent in the source, then their compiled versions have to be contextually equivalent in the target. So that's equivalence preservation, downwards. And equivalence reflection is the other way, that if these two target components are equivalent in, contextually equivalent in the target, then their original source components are contextually equivalent in the source language. Okay? When a compiler is both equivalence preserving and reflecting, we say it's fully abstract. It's just terminology. It's good to know because most people normally don't bother saying equivalence preserving compilation. They'll just say fully abstract compilation. Okay? Another thing to know is that equivalence reflection is usually boring. Sort of. Equivalence reflection usually is a corollary that you can prove if you have already proved your compiler is correct. Okay? I'll come back to these things. Okay. All right. So, fully abstract compilation. Yeah, so I think I've said some of this already. What we want is to compile the blue E into this purple target E. And we want to make sure that E will remain as secure as the source blue E when executed in arbitrary target level contexts. And, I've already been calling them attackers. And so we need to make sure that my attacker A here can make no more observations about E, about the target E, than any source context could about the source E. Okay, so let's talk about how we might do this. I like to put up this figure because to me it captures what are all of the programs that are syntactically possible in these languages, right? What is going on? And, syntactically possible, and then sort of what behavior do they represent? So let me sort of explain what I mean. I have a source language, and in it I can write lots of, legitimate, let's say well-typed source expressions ES. if my language is typed. When I compile them down to a target language, the target language has a lot more behaviors, right? And so that blue circle at the bottom where ET is sitting represents the image of the compiler. That when I compile code from the source, I compile into this blue bubble at the bottom. But that's a subset of all of the behaviors and programs that are possible in the target, right? So problems start to arise when we're linking with code, which I've written A for, these attackers, whose behavior sits outside of that blue circle. Right? And I want you to think of this blue circle at the bottom not just as the syntactic compilation of source programs. I want you to think of it as the set that subsumes all the syntactic behaviors of any compiled code. Does that make sense? Okay. So now the problem is that my attacker has some semantic behavior that I can't even express in my source. That's why I've put it on the outside of that blue circle. Right? So, ensuring full abstraction is about making sure that we protect ourselves from these attackers, which behave in ways that we cannot have, that source programs cannot behave in. Okay, so we want to make sure that any A that we link with, actually I sort of misspoke. Think of, I forgot my own figure. Don't think of the blue circle at the bottom as semantic. Think of it as syntactic. That's what I had in mind when I drew it. Okay, so that is syntactic, and now I'm linking with some code that did not come from the compiler. All right, and the issue is that some of this code, even though it did not come from the compiler, could be behaving as if some source code would have. Whereas there might be some code that behaves in ways that some source code cannot. Right? So we have to make sure that any A that we link with behaves like some sort of source context. So how can we do that? We can do the really dumb, naive thing, which is, let's add all of the extra features in the target to the source language. Stack? Call stack? Sure, let's add it. What else? Jumps? That seems like a pretty silly way of building a compiler, right? Your source language and your target language, there's no difference. We don't gain any sort of advantage from programming in a high-level language. So this is silly. But I bring it up because, ensuring fully abstract translations has been a topic of interest for decades now. And you will find the literature sprinkled, like there are papers where, they're talking about some small translation on some idealized language, but when it came to proving full abstraction, they said, oh, I don't have this feature in my source, I'll just add it. And now look, I can prove full abstraction. Now I'm not making fun of it, it's just that we have not had techniques for doing this, okay? And so often there are results in the literature where people have had to add that in order to sort of make progress and at least explain what form of security they might be getting even in the absence of that feature. Of course, this is normally done in fairly high-level translations, it's not at the level of adding jumps to your source. Okay, so this is bad. Next, we could add dynamic checks, which is about catching this badly behaved code in the act, stopping the program. But the problem with dynamic checks is that it comes with a performance cost. And essentially every single time you cross that boundary, it depends on how much interaction you have between an attacker and your compiled code. This could get really expensive. And this is essentially what's also happening in the whole field of gradual typing. For those of you who are familiar with gradual typing, it's this question of, when you have typed code interacting with untyped code, you want to put some checks or monitoring at the boundary, and that can get very, very expensive. There's a paper called Is Sound Gradual Typing Dead from, I believe, POPL 16 that goes into this and runs performance numbers. Okay. The third idea for making sure that you've protected your compiled code is to use static checks. And here it's about, can we rule out badly behaved code, linking with badly behaved code in the first place? All right? So in other words, if when I compile ES to ET, I have some idea of what type any attacker that I link with must satisfy. If it type checks, I will link with it. If it doesn't, I won't. Okay? But now the burden is on me. I have to craft a type translation that will make sure I do not link with badly behaved code. Somehow types have to capture good behavior. Right? Okay, so this is essentially a verification issue, right? You need types or some sort of a specification for attackers that you are willing to link with. Okay. So let's go into type-preserving compilation. I'm mostly going to talk about enforcing security using the third idea, which is static checks in the target. No one here has talked about type-preserving compilation, I take it, in the lectures last week? No? Okay. How many of you are familiar with the idea of type-preserving compilation? Oh, okay, great. All right, then I'm glad I have this slide. All right, so let me step back. It used to be that until about the mid-90s, whenever we built compilers, even for typed languages or strongly typed languages, we would end up doing some amount of type checking at, given some source program. We would alert the programmer to errors, type errors, if there were any. But then after that phase, once the program type checked, we would throw away all of the source level types and then continue to essentially compile the remaining untyped program. Okay? Now, this way of doing things obviously is completely susceptible to not being secure, right? As I've already tried to motivate. So around the mid-90s at CMU, and Bob was here last week, so Bob Harper, Greg Morissette was a student of his at the time, and several others at CMU started working on type-preserving compilation, where the idea was, hey, these compiler intermediate languages that are, that we're compiling to. So with every phase of the compiler, you are taking some source code and you're lowering to a lower level format, and you keep doing this all the way until you get to assembly, right? How about we design our compiler intermediate languages, or IRs, intermediate representations, so that they're not untyped, but rather typed languages? And then we can do the following thing. When I compile an integer down to the next pass, I can still annotate it that it has to be an integer. When I compile a function that takes an integer and returns an integer, if I'm doing closure conversion, then I can represent it as, oh, this is a closure, which means it has some environment and it's some code, but not the code part of it still takes an environment, but takes an integer and returns an integer, right? So preserving the information that you have, but sort of translating it so that it reflects, so that you still know that those things should hold as you compile to lower level code, right? Okay, so that's what this type preserving compilation idea is about, and in fact I'll go into closure conversion and show you how we do that in a type preserving way. But in general, I'm going to be writing things like this. So if you have a source program E that has a type tau, then if a type preserving compiler would produce some target code, that purple E, and it would make sure, and this would be a typed target purple language, it would make sure that E has some translation type. Okay? So I've already sort of tried to allude to what this might look like, right? You have an int to int function. You might translate it into a type that a pair of, like a closure of some code and some environment, but you give it an appropriate type for that. Okay, so tau plus is my way of writing the type translation. We could use type preserving compilation to ensure secure compilation. And the figure would essentially look very much like before, but this time I'm using types to help me out. If I know that E1 and E2 are contextually equivalent in the source at the type tau, and imagine that there's a gamma there as well, then after I compile, I want to be sure that E1 and E2 are contextually equivalent at the translation type, right? Because my compiler is translating those E's into target E's of translation type. Now this translation type ends up serving as your interface, okay? A type interface between your compiled code and the context. And therefore now that type interface, if you sort of make it tight enough, you say, oh, I don't want to accept an int, I will only accept a bool. I don't know, just to make it up, right? Then you can encode that in your type and refuse to link with contexts which are trying to pass you a bool, for instance. Or the other way around, whichever way I said it. Okay, so here's just some of the papers in the literature. This is just a tiny set of everything that's out there. There were papers on type preserving compilation that were preserving types down to sort of the middle parts of a compiler. And most of this work was coming out of CMU. And then this paper, System F to Typed Assembly Language, is a classic. If you're going to be a PL person, you must read it. It's really, really good. And please, you might not get it the very first time, but it's one of those papers that you want to read 2-3 times and get them. It mostly makes best paper lists for NPL. Okay. So System F to Typed Assembly Language. Basically, that was the paper that first showed that we can even make assembly language typed. and that it brings us certain benefits. We can rule out a very large class of errors that, otherwise we end up debugging our compilers and, in trying to find those errors. So there have been other efforts like that. So typed compilation of featherweight Java to F omega. This essentially captures the intuition that you can take private fields in Java objects and compile them to an existential type that hides the field from clients. And I'll talk more about that later in the context of closure conversion. There was a paper on Fine, which translated F sharp with refinements and affine types to DCIL, which was a dependently typed CIL. And then, there's more. There's many more. But I'll move on. Okay, so ensuring security through types. The next thing that I want to sort of jump into now lies at the heart of why this entire field is so difficult. Okay? It's not just about, let me write a compiler. Maybe I can come up with the right type translation and make sure that I never link with bad target code. If it was just that, I think we would have had a lot more results. But then if you want to verify that you have in fact picked the right type translation, and you are in fact ruling out with all target attackers that could tell the difference between your ET1 and ET2, you have to do a proof. And here's how the proof goes. Proving it is hard. And I've already alluded to this a little bit. So I have E1 and E2 at the source that are being compiled to my target E1 and E2, and let's assume I have a type-preserving compiler. What do we have to do to prove full abstraction, right? So we are given that ES1 and the source E1 and E2 are contextually equivalent. So there's no source context that can tell the difference between them, right? That's what contextual equivalence says, or same observables. All right, what we have to show is that given an arbitrary target context, it should not be able to tell the difference between the compiled E1 and E2. All right, so now here's where the back translation comes in, right? We somehow, the only thing we can do, the only premise hypothesis we have for this theorem is the thing at the top, that source context cannot tell the difference between ES1 and ES2. So somehow we have to be able to back translate our target context into a source context, and then argue by contradiction that this is not possible. Okay, so let me, yes, okay. Any questions about that? Yeah.
So,
yeah.
All right, so we were talking a bit about the dynamic checks.
Yes.
Or so isn't it like, how can we translate just the context and that should be sufficient, but we want to also translate the linking?
The linking somehow, right? Like what is the interaction between them? Yes, you're absolutely right. So the way that I've stated this on this slide is specific to assuming that I'm using type checking at the target level to rule out linking, to ever, completely rule out linking with any bad attacker. But in a dynamic context, this theorem changes a little bit. So in a dynamic context, what you do is you do allow linking with an arbitrary target, right? But in a dynamic setting, a dynamically enforced setting, that E1 and E2 are essentially wrapped with some sort of monitor or wrapper that is going to check every interaction with this target CT. Okay? And now what you have to do is you have to show that CT with wrapped E1 behaves the same as CT with wrapped E2. Okay? And in order to do that, so I can point you to a paper by Marco Petrignani and others, which is about a secure compilation result. What they do is they essentially say, they set up the formalism so that they say, let's run both until we observe a difference, the first difference, where the monitor has perhaps, sort of reported something. And then what we will do is we will take what is happening in the trace up to then and use that to construct an appropriate equivalent source level context and show that, if this sort of bug happens, difference happens, then that means I have to be able to come up with a source, and then I have a contradiction, because then my source would be able to tell the difference. But yes, thanks for the question. Okay, all right, so any other questions? I now want to move on and just, sort of dive in and start to show you closure conversion, and then typed closure conversion. This is going to be my case study. Yes?
So just to understand, the back translation is the intuition that you give me an arbitrary assembly program out of LinkedIn, and I need to back out the ML code that would have generated that and then compare that?
It's not that. So a back translation can't be a decompiler. This is not what we want to be able to do. We basically need to show the existence of something equivalent, behaviorally equivalent. So, in other words, you want to be able to show that if you have some target context, normally you set up some sort of equivalence relation between source and target programs. And this doesn't need to be an algorithm. That's why I don't like calling it a decompiler. It doesn't need to be an algorithm that takes that code and produces a source context. It needs to be some sort of, you basically need to show that, such a context exists rather than actually cough one up, so to speak, if that helps.
That's useful.
Okay.
That also seems that sort of would be self-defeating in some example. It seems like a really useful application is when you link against external code, often because that couldn't have been expressed in the source language, right? This is really true about performance libraries, we're using crazy assembly intrinsics, and so if you require that code could have somehow been expressed in the source language, then that you wouldn't have been linking against it.
So this is a great question. So your premise in that question was that you want to link with code that is really low level, but is your intuition that it's perhaps more efficient than something I could write in the source, but its overall behavior is still expressible in the source? I could write it in a much less efficient way in the source? I'm asking because there are two scenarios here to consider.
Yeah, I think that's usually the case. More like it relies on some semantics that are difficult to express in the source. Like this is a common problem in Rust, right?
Yes.
Various kinds of memory management stuff that's easy to do in C, but tricky to express in Rust.
Yes, exactly. So you've moved to unsafe code. All right. So the idea here is, let me give you a concrete example. Let's say I have a source language, and we'll make it simple, right? Let's say I have a source language that does not have exceptions. And I want to compile down to a target language, and I want to link with some code that does throw, I have exceptions in the target language. So my target code can throw exceptions. Now the problem is that if that exception travels across the boundary from the target code into my code, then I'm going to have a problem. I will show you an example tomorrow where that causes, this equivalence preservation to fail. But I would really still like to be able to link with some target code that internally throws the exception and then handles it. Now, of course, that kind of behavior can't be captured in the source, it seems, right? At least it can't be decompiled into the source. Okay? This is a very important thing. Even though it cannot syntactically be decompiled into the source, because the code is internally throwing the exception and then handling it, what I'm saying is that the end-to-end, the external, extensional behavior of that component can still be expressed in the source. Okay, so I'm talking about a semantic notion of, I want to be able to link with all sorts of funky code, but I just don't want it to do bad things across the boundary. It can do them internally, it can be super efficient, and that's the dream. How do we link with that? And capture semantics extensionally rather than, get caught up in the syntactic details. Okay? Any other questions? Yes?
So can I consider that the
Back translation?
back translation?
Yeah.
Can I consider the back as so kind of like I/O point-wise between context?
Yeah, I mean, at the end of the day, what you want is that if you want to think of behavior as traces, right? Traces of observable events that you can see. And even here, there's some magic in how you set up what are the observations that I can see from my language. All right, but if you think of, I'm running some target code and there's some way that I've defined what behaviors or events are observable, you want to show that whatever is observable in the target is exactly, is observable in the back translated source. Like that's the sense in which you want to produce something equivalent. But because I'm sort of now stepping away and saying observable behaviors need to be the same, the details of how those observable behaviors arise and what happens internally, those hidden behaviors, they can be different. I don't care, right? And then the techniques for actually proving this stuff does not even need to involve traces. Sometimes it does, sometimes it doesn't. Yeah.
If you read context as a function,
Sorry, if you, what context?
read a context.
Yeah, context is a function, yeah. Yep.
And in programming language with first class continuation, the context is just a function.
Yep.
And if we consider it this way, is it like, is it saying two contexts are equivalent, just like saying two functions are extensional equivalent?
Absolutely. So, in fact, in the proofs that I've done, and one that I will show you, this context can be modeled as just a function. Like technically, I have papers in which this is precisely what we do. We say, oh, now I have to back translate this. Well, this can be thought of as this sort of a function, lambda xc. Now it's a function, so let me just, if I can translate all functions of that shape, then I'm good. So then we start translating arbitrary expressions. Back translating arbitrary expressions rather than saying only contexts. Yeah. So the intuition is exactly that. It's basically a function. Any other questions? Yeah.
So can we think about this problem in a bisimulation perspective?
Uh-huh.
So if I choose a program in source language and target language both as to automaton, and some state of the automaton are equivalence, or we say the uninference. And after the operational transformation, we move to another state, and they also have the same property, and we link some states from source language and target language use bisimulation method.
I think you should totally be able to use bisimulation. I'm not sure exactly of the details of what you suggested. I would have to think a little bit more. But the kinds of techniques I'm going to show you logical relations, which are a way of proving equivalence. And, bisimulation is another way of proving equivalence. So, yeah, there are many different techniques that one can use. It's just that in the end of the day, whatever formalism you're using will probably involve some sort of, technique for proving an equivalence property. Okay? All right. Okay, so let's switch and talk about closure conversion. What do I have to do here? Do I just switch off pre-2? Yeah.
So when you said earlier that you need to show the existence of a representation of the source language, but not necessarily provide one itself.
Yeah.
I guess the thing that I'm having trouble understanding is so for example, if you in theory or something, if you give them a hardness reduction, right? It's once you showing the existence of a solution is sort of similar to giving the solution.
Yeah.
It's
Yeah.
very
I knew I was getting myself into trouble when I said that a little bit because it's not precise. And the answer sort of is that it depends on how exactly you are doing your equivalence preservation proof. So can we come back to that question maybe tomorrow? Okay. All right. That doesn't seem to be turning off. Power. Oh, okay. So just turn it off? Okay, so closure conversion. So closure conversion is a technique that essentially takes functions which might have free variables in scope, caught up in their environment, and turns them into completely closed code. All right. So, for example, if you take something like this code here, if you have let x equals 1 and let y equals 2 and let f be some function that takes, let's say, a w. I'm going to make a type. And basically does x plus y plus w. Right? So this function f here, what free variables does it have? Right, x and y are both free, right? They're caught up, they're free in this function, and what we want to do is we want to take functions like this and convert them into closed code. The reason that a compiler needs to do this is that functions are then going to be hoisted up to the top level, and eventually in another compiler pass, they're going to be allocated on the heap. because functions are too large to actually live in registers, for instance, right? So you want to be able to allocate them on the heap. When you allocate them on the heap, there's no notion of scope, right? I won't be able to say, oh, this is a function that's sitting in my heap, and by the way, it has in scope x and y. Right? So that's the intuition for why we do closure conversion. Right? We need to turn these functions into closed code that can just sort of exist on their own and be allocated on the heap. All right, and then we might do something like f applied to 100 or whatever. Okay? So there's a program. So now, when we do closure conversion, the idea is that every function in the original code needs to get turned into a closure. All right? And a closure is a pair. It's a pair of code paired with some environment, right? So for this particular function, that's f over here, what I would do is I'm going to write a new function, the code, which takes an environment as input, and that environment will be the thing that provides the values of x and y, okay? So, actually, let's transform the whole thing. So essentially, that program ends up getting converted into let x equals 1, let y equals 2, in let code be something that takes an environment, so let's call it z, this is the env, and something that pair. I'm going to rewrite this code so that it doesn't just take the w as an input. It first takes an environment as input and then takes a w. And then what it does is it's going to project out the x and the y better be in an environment, which we'll get to in a second. And then we're going to project out y from and use them where we need to in the body. All right? So essentially what I'm going to do, actually let me write env first, just to show you. So I'm going to represent the environment for this as just a tuple, x and y. I need those values, right? So the idea is that I want to be able to pass this environment as an input to the function rather than so that it can be locally closed. Yes?
What's the subscript like that? See?
Oh, I put env there just to remind you guys that this represented the environment. But I can just write z as well. Okay, and then, oh, sure. How much larger? Is this good? This line?
It's a little small, but it's okay.
I will redo. Is this good?
Yeah.
Okay, code, yes. Take the z, I'll just write z this time. W, do stuff. The environment will be x paired with y. This is a tuple, okay? All right, how do we rewrite the body? Well, I don't want to use x and y. I want to use the x and y that are now in the environment. So what I'm going to do is say, let's use projection. Project the first thing out of the environment. That should give me my x. So pi 1 of z, pi 2 of z, and w. Okay? And then f now gets represented as the pair of those two things. I'm using angle brackets for tuples. Okay, and finally, we are going to apply f. Before we were just applying f to 100. But now f is not just a function. I can't just apply it. It's a pair. So I have to project out the code. Okay? F is a pair, so I project out the code. I project out the environment and pass it as the first input. And then I have to pass in 100. So f applied to multiple arguments, right? Or the code applied to multiple arguments. Does that make sense? Okay, so pull out the code, pull out the environment, pass the environment as the first input, and the order input as usual. Okay, so that is closure conversion. We have taken this code, and now, f is just is a closure. It's a pair of a code in an environment. You can go allocate it on the heap, and it's completely sort of local, right? I mean, it doesn't have any scope issues that we need to worry about. Okay, so the interesting bit about closure conversion is that there's an idea that this environment is hidden inside the closure, that it's local to F. It is the thing that will always be passed in as the first argument. We really, really want that, right? But as I've written it right now, I'm doing closure conversion. Let's say this language was typed. I'm doing closure conversion, and let's say I'm translating it to an untyped language. Okay, seems fairly okay. I haven't done anything wrong. There's just no types on that side. But yet, this transformation that I've done, I have this invariant in my head that whenever a function is now written as a pair of a code in an environment, it is that environment that is the only thing that should ever be passed to F as the first input. So already you should be worried about secure compilation, right? I'm insisting that my environment should be hidden in my closure, but it's not. Because some other code, if I take this F and pass it to someone else, to a context, the context can pull out the code, project out the first piece, and pass it some environment of its choosing. It could pass in an empty environment, or it could pass in an environment that only has one thing in the tuple instead of two, right? And if a context ends up doing, pi 1 of F and then applying it to this together with some other, let's say 100, what's going to happen if a context does that? Pi 1 of Z got a 5. Pi 2 of Z got a doesn't exist, right? Okay, so at the very least, a context can now use my closure in a way that, is not sensible, and programs can crash. You can do other things too. I was trying to think of examples like, suppose that this function F is something that I've crafted so that it takes some input and does some really, does some crypto kind of computation or something, and perhaps at the end produces a certificate. Okay, but the function that I wanted to write, it has some variables in the closure. Maybe these are secrets, maybe these are important and special, right? And they are built into what the function is doing. This function up here is an add 3 function, right? Because it's taking 1 and 2 and adding them to that function. But now you, the context, can take that code and you can turn it into an add 42 function, if you like. You've changed it. Right? And maybe it still at the end produces the certificate. Yay. So you can do bad things with this kind of thing if the environment is no longer kept hidden. And if you just sort of step back for a second, what is going on? We were in a high-level language. There was no way for a context to figure out what is in the environment of a given function. You give someone F, they have no choice. All they can do is application. They can pass in an integer and stuff happens. Right? They don't have a handle on that X and Y. They have no way of peeking in and looking at it or changing it, right? Which is worse. But now the process of closure conversion, it's actually, as many compiler transformations do, you take something high level, but then as you do a transformation to lower level code, certain things become manifest. In this case, the environment has become manifest. And the context has the ability to sort of go in there, reach in there, and change it and tweak it, right? So we are making behaviors possible that were not possible earlier, right? So how do we fix this kind of thing? Well, so I'm going to show you typed closure conversion. This is due to Minamide, Harper, and Morissette. And it goes back to a Popple, I believe, 96 paper. Right? They were the ones who first came up with type closure conversion. And actually, before I even show it to you, let me show you another thing. So we want to preserve types. Okay, so maybe one thing we could do is we could just sort of assume that this is now a typed language. All right, let's do that, and then let's see what's wrong. So this is a typed language, which means we're going to do this exercise of figuring out what is the type of this code that we just produced. So what is the type of the code? What type would you ascribe to this function here? Let's do environment first. What type would you ascribe to the environment? Sorry? Okay, int cross int. I'll write it as a tuple type like this. Okay, it's a tuple of 2 integers. Okay, this function here takes an environment, right? Then it takes a w, that's an integer, and then we do stuff. Okay, so the type of the function is, takes the type of the environment. I'll write multi-argument functions, takes an integer, and produces. Okay, so what's the type of f? It's a pair, right, of code and environment. So the type of f is this paired with, I'll write this cross. Right? Yeah.
But the code is not going to take an arbitrary tuple of this type, but that particular tuple.
Yeah.
We need some
We do need something, but we can do with less than dependent types. So before I even show you what we need to do, right? So what's your name? Casey. So what Casey's pointing out is that, wait, the problem that I was alluding to earlier, I have to make sure that only this environment gets passed in. Well, my type on the board right now is not helping me do that. Right, we're not there yet. Okay, the other thing that I want to point out to you is if this is the type translation that we use, right, if this is how we translate for closure conversion, then effectively we have taken this function here, which was an integer to integer function, and we have translated it to a function of this type. But now let me give you another integer to integer function. Let's call it g. This is an integer to integer function, right? I'll put int there. Okay, so when I translate that function, if I use the same kind of closure conversion trick, I will get a pair. What will the type of that pair be, of that closure be? Translated G. What will its type be? What's its environment? Empty. And then it takes an int, and then it produces an int, and all of that is paired up with an empty environment. These two do not look the same. So if you're trying to do type-preserving compilation, we already have a problem. You are taking things of the same type and turning them into things of different types. This is bad, right? It means things in terms of what kind of client's context you're going to interact with. They need to know what your environment is, right? So suddenly we're able to distinguish between them. Okay, so how do we want, what we really want is we want to be able to hide the type of the environment, all right? And to hide the type of the environment, we'll use a trick called existential types. That's exactly what this paper was about. That when we do a type translation for closure conversion, from our source types, I'll write sigma for source types. So let's say my source language has the type integer and it has functions, sigma 1 to sigma 2. When I translate them to the target language, I want to be able to use an existential type. I'll fill this in a second, but essentially I want this language to give me the facility to write types like that. Has anyone covered existential types here, or how many people are already familiar with existential types? Okay, the vast majority. All right, but I'll fill in enough for everyone else. Okay, so what I want to do is, instead of producing, giving the translation of G this type and the translation of F this type, I want to make that environment hidden, which means that I want to abstract over it. So I want to give them both the type. There is a function that takes an abstract type alpha, and alpha stands for the environment, is the type of the environment, but it's hidden. It's paired with an environment of exactly that type, and I will use an existential type to hide what that is from all clients of this closure. Okay? Did I hear a wow? No. Okay. All right. So if we use this kind of a trick, we can translate both of these int-to-int functions to a function of this type, right? With the details hidden inside. All right, so I should wrap up, I'm just going to show you just lay out the types in my target language, and then I will continue this afternoon. But let's write down what the type system I need from my target language is. So I'd like to be able to, well, do closure conversion. So I'm going to go from single argument functions to multi-argument because I need that there. So we will have int in our target language. We'll have multi-argument functions, tau1 through tau n, arrow tau. I need to give myself tuples so that I can construct those environments. Okay, and then the last bit I need is the ability to create existential types. Okay, all right. I'll stop here, and this afternoon I'll show you, we'll lay out type closure conversion. We'll show you exactly how the translation works, and then I'll show you how to prove it correct. Okay.